beta decay. The basic beta decay processes are negative beta decay, positive beta decay, and orbital electron capture. In negative beta decay, as we know, electrons are emitted. In positive beta decay, positrons are emitted. Negative beta decay is also you can call as electron emission. In this, a neutron is converted into a proton with the emission of an electron and anti-neutrino. This process is also already known to us. The reaction can be written as a neutron with the charge 0, and that means atomic number, and mass 1 is converted as a proton plus electron and anti-neutron. And in positive beta decay or positron emission, proton is converted into a neutron with the emission of a positron and neutron. Positron means antiparticle of electron. That means it is positively charged. And this reaction you can write as a proton gives neutron, positron plus neutron. And orbital electron capture. Here the nucleus absorbs one of the electrons from its nearest electron shell and it is emitting a neutron. There is no emission of proton, no emission of electron or positron. Only neutrino is emitted. And this is a pictorial representation of your electron capture. You can see that an electron from the shell, and it is found that normally K shell is the nearest shell to the nucleus. So most commonly electron is captured from the K shell. That is why this electron capture is also known as K capture. So an electron is captured or it is absorbed into the nucleus, and from there a proton is converted into a neutron and a neutrino is emitted. This is the reaction. So here only neutrino is emitted, but in positive beta decay and negative beta decay, electrons are, that means either positive electrons or negative electrons are also emitted. And regarding the energy release in beta decay, we can see that beta particles have a continuous distribution of energies ranging from 0 to an upper limit. It is found that the beta particles are not emitted with the same energy. Some have a minimum energy, that means 0, and some with the maximum. So there is a range, and the upper limit is equal to the energy difference between the initial and final nuclear states. That you can write from the nuclear states knowledge. So there is an upper limit which is equal to Q value of that particular reaction. And this is the graph. You can see that this is the electron kinetic energy. It is increasing, and this is the number of electrons. This is with the maximum, and you can see that the number decreases as the electron energy, kinetic energy increases, and there you are getting with the maximum value, say 1.16 MeV. So above that there is no, there is no electron. And what is the reason for this? A wide range. That was a question for so many years. And we know that at the initial stage, we have assumed that in a beta decay, the first beta decay known to us was the electron emission, that means negative beta decay. In that, initially we have assumed that a neutron is converted into a proton and electron, and that electron is emitted. But the problem regarding this assumption was that you can assume that reaction, neutron gives proton plus electron. We have so many conservation laws in reactions. Here you can see that when it is regarding charge, you can see that the charge is conserved. The neutron is neutral one, positive charge proton, negative charge electron, total charge is 0. And regarding the angular momentum or your spin, you can see that both or all of these three particles are half spin particles. That means neutron half spin, proton half spin, electron half spin. When the spins of proton or electron are parallel, we are getting them as 0. And when they are in the same direction, it is 1. So the spin is not balanced. That was the first conservation laws that we can directly understand as it is not obeying to. And also, in order to, so you can see that that is not the final, or it is not the correct reaction. And we have now noticed that electrons are emitted with different energies. So some people think that this is a weak interaction, and in weak interaction, the law of conservation of energy is not valid. But law of conservation of energy is valid in all cases. So, in order to overcome all these difficulties, it was Pauli who proposed that in beta decay, another particle is also emitted. And he called it as neutrino. And it has no charge. Neutrino means little neutral one. When you are observing the masses, you can see that the sum of proton and electron mass is nearly equal to that of neutron. And so we are getting as neutron gives proton plus electron plus anti-neutrino. And this anti-neutrino has very small mass, or even zero mass. That is why you can't detect it very easily. And its spin is also half. So you can see that you have three particles, proton, electron, anti-neutrino. Out of these three, two will be in one direction spin. That means they will one opposite half. So definitely you are getting it as half. So the spin is now okay. And based on the neutrino hypothesis of Pauli, Fermi put forward the theory for beta decay, and that we can discuss in the next session. That's all.